Hello and welcome. This is the first video that I'm doing in 6 months. I'm actually physically recording. So today is the 8th of June and I decided to introduce the product operator, which we don't really get to see much in straight maths. So let's first of all define. This is a capital pi. Okay, and let's see what it actually stands for first of all before we evaluate this particular quantity and talk about it. So let's say ui from I is equal to 1 to, let's say, infinity. It works very similar to the sigma operator. So I'm writing a sigma operator here. So from 1 to infinity ui. Of course, this gives a command to add, to sum. So this will be u1 plus u2 plus u3 plus u4 forever, goes to infinity, starting from u is equal to 1. And the product operator, which is a capital, this is the lowercase pi, or if you want like this is the capital, so it's essentially the same letter. It actually gives the command of a product. So it says basically u1 times u2 now times u3, so that's an infinite product times u4 times ... So let's see a few examples, some very simple examples of the pi operator. So excuse my cough, as you can appreciate, I'm not very well. So let's say, for example, pi from r is equal to 1 to, let's say, 10. So what does it stand for when we have something like that? So r is equal to 1, r is equal to 2, so it's a product, 3, this is not infinite of course, so it finishes at 10, so this is of course something we recognize is 10 factorial. What about if we had, let's put actually again another one from 1 to 10, and we put an r squared, so that is equal to 1 times 2 times 3, of course they're all squared, times 10 squared, which of course we can write as 1 times 2 times 3 times ... times 10 all squared, which is the 10 factorial all squared. And of course we can actually write more. For example, we could have 1 plus 1 over r, and we're going to have an infinite product like this. R is equal to 1 to infinity. What does it stand for? 1 plus 1 over 1, 1 plus a half, 1 plus a third, plus ... And let's do one more. Let's say we have one that involves factorials. So it gives us some freedom, that the product operator. For example, if we had from, let's say, from r is equal to 5, this quantity here is of course 5 times 6, because we start from 5, remember it's always product, times 8 times 9 times 10. Can we write that perhaps as a factorial of some sort? Of course we can. We can actually insert is probably the better word to use, top and bottom, another 4 factorial. So what I'm writing now in the second bracket is what was already there, that's this bit here, and of course at the same time divided by 1, 2, 3, 4, and of course this will be a 10 factorial on the numerator divided by 4 factorial. So this particular product is equal to that. So let's return now to our problem, which is to find, or rather evaluate, the question says, this particular quantity. So we have to assume this particular, because it's an infinite product, converges into something. It's in fact very simple, and I just use this very ugly looking but very simple example to introduce the product operator. So let's see what this actually stands for. So let's write a few terms explicitly so we can actually see it. So when r is equal to 1, this will give us e to the, and that's going to go, of course, 2, so it's going to be positive, to the 1 over 1. So that's basically E. Plus E, we're putting in now R is equal to 2. That's going to go negative. And now we go negative a half. And remember, I already made a mistake. I put plus, it should be times, of course. It's a product operator. And that was not deliberate. That was actually a genuine mistake. So you have to be very careful. And now it's going to go to a 3. So that's going to be to the 4 there. So it's going to return back to positive. So the terms will alternate. And at the bottom, we have 3. So we can actually see the pattern of what we are going to get times ... forever. So now this is actually quite simple because these are exponential, so they have a special property. So I can compact them into a single quantity on the exponent, 1 minus a half plus a third minus a quarter plus ... This is a very well-known series on the exponent. If we look at the Maclaurin expansion of the log of 1 plus x, which of course is x minus a half x squared plus a third x cubed minus a quarter x to the 4 plus ... And this is valid between 1 and minus 1. We can have equal 1 but not equal to minus 1. And if we substitute it here, x is equal to positive 1, which is of course one of the allowable values. This will convert to 1 minus a half plus a third minus a quarter plus a fifth plus ... So in fact, this particular expression that we have after we got rid of the product operator, this bit here, is in fact e to the log 2. And in fact, the value that we're looking for, this particular one, is in fact equal to 2. Just only 2 lines of work. I hope you understood a little bit how the product operator works and you find it useful. I will try in the future to give you more practice with a few more problems involving this item. For the time being, I'm signing out and I hope you enjoyed this.